Hello. So it's 4 o'clock in the afternoon. It's quite dark outside already, but that's because you can see the back of the room is dark. So let's get on with problem 9. So it's a dry run dealing with logarithm and exponential function as a complex function. And the usual way is to start defining the exponential by its series and then taking the theory from there. In this problem we do it the other way. We define the logarithm as a path integral, and then we have to do some stuff. So it's defined for a simply connected region. We'll just draw it. Let's do that down here. So the complex plane and the function we are working with is 1 divided by z, which has a simple pole at 0 with residue unity. And now we have a simply connected region not including the origin. For instance, this may go many ways around. And then we define log as the path integral. First they go from unity to some point v0 in here. And then we go to another, staying within that region. Show that different paths, the function changes by a constant value in the lattice. Of course, the path, I don't get that. Oh, that must be a different path going from unity to v0. So, if we take another path from, that's from unity, of course. So if we take a path that goes around here up to v0, instead of the blue one going from 1 up to v0, then the difference will be a multiplum of 2 pi m. So I'll just correct the first path here. There we go. So the first path goes like that, and the second path like that. Yeah. That was actually a poor picture. We'll just do it better. We have unity here and V naught here, and then we have two different paths from unity to V naught. So this part is called, what do you call a path really? Set of t, Z1 of t and Z2 of t. So first, the definition that it's well defined. So when we have a choice of the first path, then we'll always get the same result. And that's because we are in a simply connected region. So any path to V, or any two paths to V, can be it's a standard argument, but I'm not really sure how to put it succinctly. If we have two paths going from V naught to V, pipe 1 and pipe 2 going V naught to V, then combining them, I don't know how you combine paths, let's add them. Then you get a closed path. And it's null homotopic. And V naught is distinct from the center, from 0. So it's there is a continuous it's not homomorphism. There's a continuous map connecting it to giving the integral 0, meaning that the integrals over these two paths are the same, so therefore log 1 will give the same result. So the difference must be different choices of path from unity to V naught. And the same argument, then we can get a path from unity to unity. And then we use the residue theorem that the integral along those paths from unity to unity equals the 2pi times the residue times the number of turns and the residue equals unity. And they call it M, all right. B. Express the derivative and in terms of V. Z is a function of and then the other one is the reciprocal. Oh, then we need to show that the usual series definition is the inverse how on earth do we do that? Oh, the usual series definition converges everywhere, etc. So differentiating it gives itself so it fulfills this one, and that means that one is a constant time the other. I should actually have written V all the way here. So V as a function of Z equals a constant times X of Z. And now the problem is that that naught is not in here necessarily, so I can't take a special value to determine C. So what can we do about that? We know, of course, that the exponential is periodic with period 2 pi I. Well, that doesn't help us. Well, we'll have to leave that for a while. Go to D. Show that the map and the inverse map here gives a one-to-one correspondence between C modulus L and C except the center. The additive group law becomes what group in C minus naught? That must be the with multiplication, of course. So that means it's stratified like this. And such a guy here is mapped into this. So how do we handle addition within this guy? That's normal addition, and this is normal multiplication. It's no problem. Because this is just adding two numbers in here will give a number up here, say, and then that is transported back into here. Wow. They are collapsed together, all the points. Mm-hmm. So are we supposed to be using the it's just a one-to-one correspondence. It's not that we should be taking any structure. Oh, it's a group law, yeah. Becomes so I would use this well-known guy. To say that to establish that. Now what I don't like here is that we the question of definition here. Yeah, that's what has been bothering me from the beginning. We have a simply connected region, and then we define this function, and it's not necessarily defined for all complex numbers. That's what's bothering me. So to use this argument, we need to be able to find a way from our region down to unity that does not go through the center, no, not through 0. That should be very possible. Except it might be dense around 0, so every path will cross it an infinite number of times. That means that this path doesn't necessarily exist. Now that's quite interesting. So as a dry run, it does seem a bit wet, the way I see it, really. If it's a compact region, a region is normally open, then I would be able to find a path down to unity. So where obviously we then have Z of unity vanishes, and then C would be unity here, and then we are home. So we have being a group with addition, being isomorphic to C minus naught with multiplication by log and going that way and exp going that way. So I hope this is sufficient for a dry run, because the problems I encountered I weren't quite able to solve. But let's that be it for the moment. Maybe I'll make an addition later.